In this video, we'll introduce the main ideas behind confidence intervals. The general motivation here is this. Confidence intervals provide a tool for using data from a sample to make inferences about the broader population. Consider an example. Suppose candidate A is in a two-way race for president. Using data from an exit survey, a polling agency reports that 55% of adults support candidate A. Of course, this estimate of 55% is just the agency's best guess of the support among the broader population of adults. That is, there's definitely error in this estimate. And without a sense of the potential error, this estimate is neither helpful nor trustworthy. For example, if the potential error in this estimate were small, as represented by the black bar here, this survey results would provide evidence that the support for candidate A is above 50%. Thus, they'll likely win the race. It could also be the case that the potential error in this estimate is quite large. In this case, the survey results wouldn't provide much insight into whether candidate A will win or lose. But the issue is that without knowing what scenario we're in, or understanding the error of our estimate, we can't put any stock into the agency's estimate. Luckily, responsible polling agencies do report the potential error in their findings. For example, suppose the agency reports with 95% confidence that their estimate of candidate A's support has a 3% margin of error. This potential error expands the pollster's findings into a range of plausible values for candidate A's actual election support. This range is obtained by taking the pollster's original estimate of candidate A's support, 55%, plus or minus its potential error, 3%. By plus or minus, I mean that we want to separately subtract and add the error relative to the estimate. This produces a range from 52 to 58 percentage points. Let's step back a moment. We started with 55%, the pollster's estimate of the overall support for candidate A. Since this is just their single best guess, we also call this a point estimate. We then calculated a range for candidate A's support from 52 to 58%. This range is what we call a confidence interval. Recalling that the pollster reported their estimate with 95% confidence, we can interpret this interval as follows. We can be 95% confident that the actual support for candidate A is somewhere between 52% and 58%. Importantly, even when accounting for the potential error in this survey estimate, these results, or this interval in particular, suggests that candidate A's support exceeds the 50% threshold needed to win the election. Now let's generalize these concepts outside the election setting. First, let beta be some feature of the population that we're interested in. It could be a mean, a model coefficient, an R-squared value, and so on. Then let beta hat be an estimate of beta that we calculate from a sample of data from that population. Since this estimate is definitely wrong, it's also important to calculate a confidence interval for beta. In general, a confidence interval reflects the potential error in our estimate beta hat, while also providing a helpful range of plausible values for beta, not just our best guess. This confidence interval can be calculated by taking our estimate beta hat plus or minus some margin of error. Right now, calculating this margin of error is a bit of a mystery. However, clues are provided by the central limit theorem. To this end, recall that different samples can produce different sample estimates beta hat. However, so long as the sample size is big enough, these estimates will be normally distributed around the actual population value beta with some standard error. The formula for this standard error depends upon a lot of factors, such as what we're estimating, how much data we have, and so on. This makes the formula formula complicated, and so I'm not going to include it here. Now, in practice, we don't know what the actual beta value is. If we did, we wouldn't need to estimate it. That means that we can't know for certain where our estimate falls on this spectrum. Our estimate might be close to the actual beta value, or it might be one of the unlucky estimates that falls in the extreme tails of this sampling distribution, up here or down here. But what we do know from the 68, 95, 99.7 rule for normal models is that there's a roughly 95% chance that our sample estimate is within 2 standard errors of beta. Thus, to calculate a 95% confidence interval for beta, we can take our estimate plus or minus 2 standard errors. For example, suppose our estimate is represented by the red dot here. Tacking on 2 standard errors to either side of this estimate provides the confidence interval range represented by the red line. It's important to keep in mind that there's also error in this process. Mainly, the term 95% confidence reflects that this method produces a confidence interval that covers the actual beta value only 95% of the time. For example, given that the estimate represented by the red dot here is so close to beta, its associated confidence interval does cover beta. That means this confidence interval worked. Though the estimate represented here is further from beta, it's still within 2 standard errors. Thus, its associated confidence interval still covers beta. That is, it still works. The same is true of the estimate and confidence interval here. However, if we get an unlucky sample that produces an estimate that's more than 2 standard errors away from beta, its associated confidence interval will not cover beta. In this case, the estimate and confidence interval would lead to misguided conclusions about the population. With this in mind, since we don't know the actual population value beta, we can never be certain whether our sample is one of the good ones that produces a 95% interval that covers beta, or if it's one of the unlucky ones. Mainly, there's a 95% chance that we got a lucky sample and a 5% chance that we didn't. Finally, to bring this concept to life, consider how we apply these ideas in statistical modeling. For example, suppose we want to explore the relationship between penguin flipper lengths y and bill lengths x, both measured in millimeters. Since we can't go out and measure every penguin in the world, we can't know the actual population model of this relationship. But we can estimate it using data on a sample of penguins. To this end, consider the following model output, calculated from a sample of 344 penguins. From this output, notice that our sample estimate of the bill length coefficient, beta 1, is 1.69. Further, the next column over indicates that the potential error in this estimate is 0.105. Mainly, the typical sample of 344 penguins would produce a coefficient estimate that's 0.105 units from the actual beta 1 value. Combining these results with the confidence interval formula from the previous slide, we can calculate a 95% confidence interval for beta 1 by taking our estimate plus or minus 2 standard errors. First, let's plug in our estimate and standard error. Next, after doubling the standard error, the total margin of error for our estimate is 0.21. We can then subtract and add this value, this margin of error, from our estimate, producing a confidence interval that ranges from 1.48 to 1.9. Let's consider what this means. First, based on our sample of 344 penguins, our best guess was that the bill length coefficient was 1.69. However, when accounting for the potential error in this estimate, we're 95% confident that the bill length coefficient beta 1 is somewhere between 1.48 and 1.9. To translate this in the context of penguins, it's important to keep in mind the meaning of this coefficient. It tells us about the rate of change in flipper length, y, for every 1 millimeter increase in bill length, x. To that end, we're 95% confident that for every 1 millimeter increase in bill length, the typical increase in flipper length is somewhere between 1.48 and 1.9 millimeters. These are big ideas, or the big ideas, behind the confidence interval. In the future, we'll come back to discuss the details. What exactly does 95% confidence mean? What happens if we want to increase or decrease our confidence level? And how can we use confidence intervals to test hypotheses about the broader population of interest?